This is Learning Assessment Problem 715. The problem-solving strategy here is the solution of a second-order transient circuit. We have both a capacitor and an inductor in this circuit, so we would expect the response, which is the voltage VO of t, to have a second-order nature. The switching occurs when this switch moves from position 1 to position 2 at time equals 0. This disconnects the 2 ampere current source from the circuit. So for time greater than 0, we have just a passive circuit response, and we are asked to determine the voltage across that 2 ohm resistor. So we'll begin labeling some terms in the circuit. So we have labeled the inductor, the capacitor, and the resistor voltage polarities assumed for the moment. First step might be to determine some initial conditions for the inductor and the capacitor. We'll take the time equals 0 minus. Assume that steady state prevails at that time, and therefore the capacitor will look like an open circuit, and this will give the result that IL at 0 minus is equal to 2 amperes. That is the strength of the current source in the circuit. Since VL at 0 minus is equal to 0 by that steady state condition assumption, we have that the capacitor voltage at 0 minus is also equal to 0 because the inductor essentially short circuits the capacitor. Now for t greater than 0, the switch is open to position . Now for t greater than 0, switch is open as far as our response of the circuit is concerned. We have a series RLC configuration of elements, and the appropriate differential equation would be d squared I dt squared plus r over L di dt plus I over LC is equal to 0, where the I of t that we're describing is circulating in a counterclockwise fashion. Again, we have V sub L Again, we have V sub L, V sub C, and V sub R in the circuit. And our I sub L happens to be coincident with that I of t circulating current. So we're going to let the I of t be of the form k e to the minus st. So we'll let the current I of t be of the form so we'll let the current function of time be of the form k e to the st. The series characteristic equation for this type of circuit is of the form S squared plus R over LS plus 1 over LC is equal to 0. In terms of the circuit values, we have R over L is equal to 2 ohms divided by 0.5 Henry is equal to 4. 1 over LC is equal to 1 over 0.5 times 2/3 farad. This is equal to 3. Therefore, our characteristic equation becomes S squared plus 4S plus 3. And the roots of that equation are S1 is equal to minus 3, S2 is equal to minus 1. We observe that the roots are real and unequal, so we can say that the circuit response is going to be of an overdamped nature. So we can substitute these discovered roots. So we can substitute the roots just determined into our assumed form of the current equation. I of t is equal to k1 e to the minus 3t plus k2 e to the minus 1t is equal So we can enter those root values into our assumed form of the current, and we have I of t is equal to k1 e to the minus 3t plus k2 e to the minus 1t, and this is valid for time greater than 0. Now what are we going to do with this I of t? We have a resistor of 2 ohm value in the circuit. The voltage VO of t that we're interested in appears across there. Our current I of t is flowing upward through that resistor, so our VO of t eventually is going to be minus 2 ohms times this current that we're attempting to discover. Now we can consider a time consider a time equals 0 plus our I at 0 plus from our assumed solution form will equal k1 plus k2. And we determine that that is the same as IL at 0 plus, which is equal to IL at 0 minus, or K1 plus K2 is equal to 2 amperes. So we need another K1 K2 equation in order to solve for those two coefficients. If we do a KVL summation, we'll go back and look at our circuit here, sum around the 3 elements in the circuit. We will have VL of t plus VR of t plus Vc of t is equal to 0. At t equals 0 plus, we have VL at 0 plus VR at 0 plus Vc at 0 plus is equal to 0. And we've said at t equals 0 plus Vc at 0 plus is equal to VC at 0 minus because of the continuity of the capacitor voltage, and that's equal to 0. So the VC at 0 plus drops out of this loop equation. VR at 0 plus is equal to R times I at 0 plus. This is equal to 2 ohms times 2 amperes is equal to 4 volts. And the result then is that our VL at 0 plus from our loop equation is equal to minus 4 volts. So we have an expression for the inductor voltage at time 0 plus. Recall that V sub L is equal to L di dt. We're going to differentiate our assumed form of the current, which is K1 e to the minus 3t plus K2 e to the minus 1t plus V sub L of t is equal to L times minus 3K1 e to the minus 3t minus 1K2 e to the minus 1t. Considering the time V sub considering the time 0 plus for V sub L is equal to 1/2 Henry for the inductance, the exponential terms go to unity and we have minus 3K1 minus 1K2, or minus 3/2 K1 minus 1/2 K2 is equal to minus 4 volts, that which we determined from a study of the loop current of the loop circuit at 0 plus. So this is our second equation in the K1 and K2 coefficients. So we can put these two equations into a matrix form. We have 1 and minus 3/2, 1 minus 1/2 times the K1, K2 matrix is equal to 2 and minus 4. This gives us that K1 is equal to 3 and K2 is equal to minus 1. That K1 goes with e to the minus 3t term, and K2 goes with e to the minus 1t term. So now we're ready to assemble the I of t expression equals 3e to the minus 3t minus 1e to the minus 1t amperes for time greater than 0. Now, as we said previously, our voltage that we're interested in, VO of t, is equal to minus 2 ohms times this I of t. This is equal to minus 2 ohms times the 3e to the minus 3t minus 1e to the minus 1t, or VO of t is equal to 2e to the minus 1 t minus 6e to the minus 3t volts for t greater than 0.